Prove each statement in 6 through 9 using mathematical induction. Do not derive them from Theorem 5.2.1 or Theorem 5.2.2. For each integer n greater than or equal to 3, 4 cubed plus 4 to the 4th plus 4 to the 5th plus ... plus 4 to the n equals 4 times 4 to the n minus 16 all over 3. So the first thing we need to do is we need to identify what our statement P of n is. Before we even do the base step, we need to carefully identify what P of n is. It's important to understand that P of n does not include any quantification. So if you notice here, this right here is a universal quantifier. So we have to exclude that from defining P of n. So this portion right here is going to be our statement P of n. So let's show that P of n is true for all integers n greater than or equal to 3. Now we can go to our base case. So the base case in this instance is when n equals 3. Since integer n is defined to be greater than or equal to 3. So that means 3 is the smallest integer that satisfies statement P of n. So let's see if that's actually true. Now I'm going to rewrite this statement where I substitute 3 into n. Now, if we plug in 3 into n, that means this last term here is 4 cubed. But 4 cubed is also the first term, which means that all of this filler terms in between are not necessary when we're writing out this series for n equals 3. For n equals 3, this is just 4 cubed on the left-hand side. So the left-hand side is 4 cubed. The right-hand side is 4 times 4 cubed minus 16 all over 3. So if we want to show that P of 3 is true, we need to show that this equation is true. And the way we can do that is we can evaluate the left-hand side and the right-hand side separately and see if we get the same results. Now 4 cubed is 64, and 4 times 4 cubed minus 16 all over 3 is equal to 4 times 64 minus 16 all over 3, which is 64. So if you notice, the left-hand side of P of 3 is 64, and the right-hand side of P of 3 is 64. So this means that P of 3 is true. Okay, next, let's get into the inductive step. This is where things get pretty crazy. What we're going to do is we're going to instantiate a letter k. So let k be an integer such that k is greater than or equal to 3, and assume that P of k is true. So the first thing we have to do is we have to define what our inductive hypothesis is. So the inductive hypothesis P of k is the same as the statement P of n, but instead of using the letter n, we use the letter k. The whole point of expanded form means that we can dive deeper into what's in between the third term and the last term. So we can say the second to last term is 4 to the k minus 1, and the very, very last term would be 4 to the k. And we're assuming that this thing is equal to 4 times 4 to the k minus 16 over 3. So we get to assume that this statement is true. We want to show that P of k plus 1 is true. Now, what does that mean? That means we want to show, which I will be using WWTS to mean we want to show. So we want to show specifically that if I have 4 cubed plus 4 to the 4th plus 4 to the 5th, and just to keep us practicing with this expanded form, I'll write out the first 4 terms. So I'll include 4 to the 6th. It doesn't matter. This is the same series, even though I'm writing out more terms. So for P of k plus 1, we need to go all the way to 4 to the k plus 1. So I'll write out the last 2 terms. So the second to last term would be 4 to the k, and the very, very last term would be 4 to the k plus 1. We want to show that this equals 4 times 4 to the k plus 1 minus 16 all over 3. That's the goal. Now, how do we do this? What we do is we take either the left-hand side or the right-hand side. I always recommend, if there is an expanded form or like some sort of series or some sort of product, I recommend starting with that side, which in this case is the left-hand side. This is a series. Another heuristic that I would keep in mind is that if you notice, this left-hand side includes the left-hand side of P of k. So this might give you an indication to start with the left-hand side, since we'll be able to use the inductive hypothesis immediately. So let's start with the left-hand side. So this is the left-hand side. If you notice, I intentionally didn't include 4 to the 6th because I buried it in here, but I just want to do that to show you that this expanded form allows us to decipher what the first terms look like and what the last terms look like, and we can be as explanatory as we want. And the more terms that we write out, the clearer it is that we understand what each consecutive term looks like and what each previous term looks like. But don't be confused, because this left-hand side is still the same as this left-hand side, even though I did not include the 4 to the 6th explicitly. It's just buried in this plus dot 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 plus. So we got to get really used to this whole expanded form here and interpreting what we can do with this dot dot dot. Okay, now let's get to trying to make this look something like that. That's the goal of this inductive step. So the first thing I'm going to do is I'm going to rewrite this expanded form, but I'm going to group together my first k terms. And that's because I can see my inductive hypothesis, at least the left-hand side of my inductive hypothesis, in this series. So I'm just going to group together this 4 cubed plus 4 to the 4th plus 4 to the 5th plus 4 to the 6th plus 4 to the 7th plus all the way up to 4 to the k minus 2 plus 4 to the k minus 1 plus 4 to the k, and then plus 4 to the k plus 1. So I'm just pulling out that last term here. I'm separating this last term from the rest of the group by putting parentheses around the part that I want to emphasize. Now, by the inductive hypothesis, we can rewrite this left-hand side as 4 times 4 to the k minus 16 over 3 plus 4 to the k plus 1. And again, I'll put on the side here, this is by the inductive hypothesis. So I'm replacing the left-hand side of P of k with the right-hand side of P of k. This is a matter of substitution. So I'm substituting the left-hand side of P of k with the right-hand side of P of k, because since we get to assume that P of k is true, we get to assume that the left-hand side of P of k equals the right-hand side of P of k. Okay, so let's go back to what we want to show. We want to show that this thing equals that. And so far, we've shown that this thing equals this mess. But we've used our inductive hypothesis. So now that we've used the inductive hypothesis, let's try to simplify this expression to make it look like the right-hand side of P of k plus 1. What I'm going to do is I'm going to rewrite the second term with a denominator of 3 so that I can combine fractions here. And I'm also going to distribute this 4. And I'm going to write everything in terms of powers of 4 so that we can factor things easily. So this is 4 to the k plus 1 minus 4 times 16, which I'll write as 4 squared, all over 3. And for the second term, I'm going to rewrite that as 3 times 4 to the k plus 1 over 3. So this is by algebra. So I'm using the distributive property. I'm also rewriting numbers in terms of powers of 4. And I'm also rewriting 4 to the k plus 1 to have a denominator of 3. That way I can combine these fractions to get 4 to the k plus 1 minus 4 times 4 squared is 4 cubed, and then plus 3 times 4 to the k plus 1, all over 3. So right now I'm just doing algebra. So now let's combine like terms. Here I have a 4 to the k plus 1, and here I have 3 4 to the k plus 1s. So how many 4 to the k plus 1s do I have altogether? That means I have 4 4 to the k plus 1s. And then minus 4 cubed over 3. And that's again by algebra. So I'll just put quotes there to signal that I'm using the same step as the one above. And the last step is we can factor out a 4 in the numerator to write this as 4 times 4 to the k plus 1 minus 4 squared, which I'll write as 16. All over 3. And so this is still algebra. If you notice, all I'm trying to do is I'm rewriting what we got after using the inductive hypothesis into something that looks like the right-hand side of P of k plus 1. So now let's summarize what we just did. We started with the left-hand side of P of k plus 1, and then we reorganized the left-hand side so that we can use the inductive hypothesis. And then after applying the inductive hypothesis, we use some algebra to change the left-hand side into the right-hand side to prove that the left-hand side of P of k plus 1 equals the right-hand side of P of k plus 1. And the only way that can be true is if P of k plus 1 is true. And now we can say that by mathematical induction, the statement is true for all integers n greater than or equal to 3. Thanks everyone, and I'll see you in the next video.